We're tackling the problem flip equivalent binary trees, which we're going to try and solve with minimum complexities of on time and on space. For a binary tree, T, we can define a flip operation as follows. Choose any node and swap the left and right child subtrees. A binary tree X is flip equivalent to a binary tree Y if and only if we can make X equal to Y after some number of flip operations. Given the roots of binary trees root 1 and root 2, we need to determine whether the two binary trees are flip equivalent or not. To visualize this example, take a look at this from LeetCode. So, with this example, we can see that we have on the left side something that looks like an optical isomer of the right side. In this case, it's true because these trees are flip equivalent. If you placed a mirror down the center of this, you can see that they'd be identical. And as is explained here, if we flip the nodes at values 1, 3, and 5, we would have an identical tree on the other side. So, let's take a look at the methods we can use to determine whether binary trees are flip equivalent or not. You can choose between A, in-order post-order traversal plus comparing, B, parallel traversal plus comparison, C, HSO algorithm, or D, canonical parentheses representation. I'm going to pause for a couple of seconds while you make your choice. So, for those of you who are able to get it, congratulations. And for those of you who just want to see the code, the answer here is D, canonical parentheses representation. Now, the brute force approach here, I'm just going to very briefly go over it. In this, we can check if the roots of the two given trees are equal or symmetric. If they are, then we recursively check their left and right subtrees and whether they're flip equivalent. The approach that we take here could take on squared time complexity because we'd be checking each node of one tree against each node of the other. So, let's take a look at how we can use this canonical parenthesis representation to minimize the complexity. Okay, so let's start with the entry point of our solution, which is flip equiv. In our provided solution code, the canonical parenthesis representation solves the problem. The trees are converted into strings using parentheses to represent the structure. Now, we're calling parenthesize canonical to do this. If the canonical representations of the two trees are the same, it means that our trees are flip equivalent. Our solution uses this recursive function, parenthesize canonical, to generate the canonical representation of a tree by traversing it in a depth-first manner. And as well as that, we've got this helper function toString, which will help us. Now, I'm going to go through this line by line, and I'm going to start with this flip equiv function. So, we're simply calling parenthesize canonical for both root 1 and root 2, and then comparing them. That is, comparing their canonical representations. If they're equal, we're going to return true, otherwise we return false. And that's it. But wait, there's a little bit more here with the parenthesize canonical function. So let's show you how that works. Well, we're taking in a tree node pointer as our input, and then returning the canonical parenthesis representation as a string, which is down here. The first thing we check is whether the root is null pointer or not. If the root is null, that indicates an empty subtree, So our function returns an empty pair of parentheses, just like this. Otherwise, we're going to be checking the left and right subtrees. So we call parenthesized canonical for the root's left and right subtrees, storing them in the strings left and right respectively. So these will store the canonical representations of the left and right subtrees of our root. To ensure the order of the subtrees doesn't affect the result, the code checks whether left is lexicographically greater than right. If it is, then we're going to perform this swap operation, and this is really key here. After we've done that, our function returns the canonical representation of the current code by concatenating the value of the node itself, the left and right substrings, and enclosing them in parentheses. This helper function is used to convert whatever integer value is for root val into a string. Let's take a look at how that works. So, we simply use the oStringStream class to create an object OSS. We feed the integer into that, and then call the str function on it to return the string version of the object. Anyway, after we've returned the canonical representation of the current node by concatenating the value of the node left and right inside parentheses, we'll be able to check whether root 1 and root 2 are flip equivalent. If the canonical representations are the same, then we know we have flip equivalent binary trees. So I hope that that's clear, and if you've struggled to understand what's going on, I'm going to recommend that you check out this course, which is in the description to this video. Obviously, the application we're launching is focused mainly on identifying the correct method to use, and at least be able to explain it. And in this case, from among these options, you should remember we can use canonical parenthesis representation to solve flip equivalent binary trees. There is an explanation here that you can choose to read through and understand in your own time. And if you prefer reading through code, we have it available in C++, Python, and Java. And at the time of the app's launch, these were able to make it through the various LeetCode test cases. So that's everything. Thanks very much for watching. And if you're following us using the learning mode on our application, then the next problem is going to be lowest common ancestor of a binary tree. A slightly different kind of challenge.